Namaskar my dear friends. So as we have been seeing switching regulator training, so we have seen already two ICs. This will be the third IC. Okay. So as I have already promised you to give you three ICs applications so that you have a proper understanding of how to read the data sheet of a switching regulator, what are the parameters that we need to like quickly see from the data sheets so that we can design our power supply regulators very efficiently, very quickly, and like very efficiently as well, and there is no error at all in the design. So that what are the parameters that we need to read about the data sheet, and what are the specific information that we should always look into from the data sheet. That's the main agenda for this particular sessions. Okay, so what we'll do is we can have an application of this ADPL13602 IC, which is a synchronous step down switching regulator, and we'll try to understand what are the applications and what are the informations that we should quickly read out from the datasheet to design our switching regulators. Okay, so as you can see, we have already seen LT3970 applications, then LT8604 applications. Now we'll try to understand ADPL13602. Okay, and I understand that with these three applications, with these three ICs, details and like design analysis, you will be able to apply and extend the same concepts to your other applications or other ICs, whichever like manufacturers that you take, whether it is Texas Instruments, or you take Analog Devices, or you take Renesas, or many more are there, like Microchip and STM. So many manufacturers are there, even Monolithic is there. Okay, so let us quickly concentrate on this particular IC, which is ADPL13602. Okay, so what are the applications that it can be used for is it has a industrial control power supply application, or distributor supply regulations, or wall transformer regulations. Even a very high voltage input is there on a single board. So there also, if you have to have a power supply system, you can utilize this particular IC. Okay, so as we open the data sheet, you can see it is going to take the input from 3.5 volt to 36 volt, and it has a capacity of very good like current rating. So earlier two ICs we saw was around like 350 milliamperes and 120 milliamperes. Let's say 350 milliampere and 120 milliampere was there. One was like LT3970 and one was LT8604. Now we are going to see ADPL1306, which has a capacity of 2.4 ampere. It is very high efficiency synchronous step down DC-DC converter. Okay, good. So with this, what we can do is we can quickly get into the data sheet. But before that, what I'll try to make you understand is what are the design parameters that we basically need to design the switching regulator for our required V output. Okay, so basically we need to have an understanding what is my input voltage, what is my output voltage, how to select the inductor, okay, for the particular like V output and I output ratings, and my switching frequency that we have decided to work upon. Okay, then how we can design our feedback resistors divider so that we can regulate the output voltage to a proper value, to a very accurate value at the output. How we can select input capacitor, how we should optimize the output capacitor values, and how we can set the soft start, like so that our startup will not have any like ringing or something like that. That can be avoided so that it can have a very smooth start. So that's the reason we want to have a soft start. How we can have proper enable input, or we can set the under voltage lockout settings, and what is the functionality of reset or something like that in this particular IC that we are going to see, which is ADPL13602. Okay, good. So as you can see very quickly from the like simplified application diagram, so this is application diagram that is given in the data sheet at the first page itself. So we have input voltage, we have enable pin which is directly connected, we have my C input like input capacitors, we have output capacitors which is C out, and we have a feedback pin which is going to connected with our resistors, let's say R1 and R2. These are the feedback voltage divider resistor which is going to set your V output. We have a inductor which will be like selected, and at the same time we are going to have bootstrap capacitor, and then we have our feedback pin we already explained. We have external voltage that can be taken out. We have soft start pin, and we have VCC that will be used for your internal purpose. So these are the different parameters that we need to design it quickly from the data sheet. Okay, so let's go to the product page of this particular IC. You can open analog.com and you can try to type from the search box ADPL13602. Okay. So once you see that, you will be having this particular page where you can see there are various part details which you can see, like we have the application diagram, we have the part details, we have some more applications, something like that. Okay, as you can see we have proper features and everything. Then we have additional details. If you want, we can read out about the applications where it can be utilized, that is recommended from the manufacturers. Okay, and even we have evaluation board also. So if you want to have exact design, you can download this particular evaluation kit and you will be getting your schematic diagram as well. But anyway, we will be discussing this during our design analysis through the data sheets. So once we click on this view data sheet, what we'll get is we'll have this data sheet ready with us. Now we'll just proceed with. Okay, so let us see that we have the data sheet available with us, which is ADPL 13602. The very first thing that you should concentrate while designing any circuit is read about all these features that is given here. Okay, so once you see that it has a reduced external components and total cost, so cost is very less and it will be very less number of components will be required to have a very good switching regulator design. Okay, and only ceramic capacitors can be utilized to have a very good design. There is no need of electrolytic capacitors. Okay, so the design will be very compact. Okay, like very small size you can design a very good regulators. As you can see, we have the very wide input voltage. So if you want, you can have a like a 5 volt input, or let us say 10 volt or 12 volt input, even 15 volt input, or 24 volt input, or 36 volt input also you can go ahead. So these are the standard voltages that are available during our board designs. So you can use any of these voltage ranges. Okay, it can have a adjustable frequency range up to 400 kilohertz to 115 kilohertz, that is 1.5 megahertz, and it can give you up to 2.4 ampere of output current. Okay, now let us talk about it is telling you about the output voltage range setting. So it can start from 1 volt settings to up to 90% of V input. Let us say you have a 12 volt input, then you can say burn what होता है, that is 10.8 volt output you can set at the output side for this input. Okay, efficiency you can reach up to 95%. We have very wide like 2.4 volt to 12 volt bootstrap bias input for your improved efficiency. And then we have like operate reliably in advanced industrial environments. Like what are the advanced industrial environments? Like you have hiccup mode overload protection, we have adjustable and monotonic startup. Okay, we have built-in output voltage monitoring with reset. Okay, so there is a reset pin. We have programmable enable and under voltage lockout threshold. We have wide industrial like temperature range which can go up to 125 degrees centigrade from minus 40 degrees centigrade onwards. Okay, good. So these were the like features that you have to take into account while reading the data sheet very quickly. So it has around 28 pages of data sheet, and what we'll do is we'll quickly understand what are the information we need it, and so that we can design our complete circuit in less than an hour. Okay, so as you can see, applications we have already talked about. We have already talked about simplified application diagram, and we can see that you have efficiency versus load current. So as my load current increases, my efficiency curve you can see. So input voltage is 12 volt, then efficiency is bit higher. If input voltage is little bit higher, let's say 24 volt, then the efficiency has reduced a little. Okay, so you can see this efficiency curve is given for 5 volt output. My V output is actually set to 5 volt from either 12 volt input or 24 volt input. Okay, and as you can see, around around 500 milliampere current, it has the maximum efficiency, and more than that, as you go on, around 2.4 amperes of current output, it has the efficiency more than 90%. Okay, so this is very good one. Okay, let's get into the next parts. So the the most importantly, why I have taken this particular IC to explain you is it can be utilized for your new design as well, because it has been recently released in December 2023. Okay, now let's get into the next one. Coming back to the electrical parameters. Okay, so as I already explained you, the input voltage that you have to keep in mind, let's say 3.45 volt to 36 volt. So if you have a system of, let us say, 12 volt or 15 volt, this IC will be most applicable or most suitable for your design. Even 24 volt system, it will be a good idea. The other parameters that we need to talk about is my enable voltage. So enable voltage will be required 1.25 volt. Okay, so 1.25 volt if you give or more than this, then you can switch on the IC, otherwise it will be in shutdown mode. Got it? Coming back to the VCC output voltage range, so VCC, there is a linear regulator, so which is going to give us 1.8 volt, but the thing is this VCC output cannot be utilized for our external applications. It is just for your internal IC functionalities. Okay, so you don't have to load with your external circuitry. Understood? Coming back to external VCC operating voltage, so if you want, you can add a 2.5 volt to 12 volt voltage supply to this pin, otherwise you can leave it open also. So that I will tell you how to read this particular data sheet to understand all these parameters that I have I have been telling you, because I already know several I have designed several switching regulators where I understand what are the pins and what is their functionalities, and we have designed this these switching regulators for many applications in our projects. Coming back to the next parameters, we have like a high side N MOSFET resistance, low side N MOSFET resistance, that you don't have to worry about, these are like general values. So if you want to have a very accurate design, high accuracy design, then you may need to know these parameters, but it is really not needed. What is the needed is I need to have feedback regulation voltage, so which is 0.6 volts. So this you keep in mind, or this you make a note of it, like I have to have 0.6 volt at the feedback voltage. Got it? Then there is a current limit threshold at the MOSFETs, which will be 3.4 amperes, so which will be required to have the ripple current settings like delta IL, or we have to have inductor current setting or something like that. So at that time this peak current limit is actually needed. Got it? Okay, we have two modes of operation, like DCM mode and PWM mode. Okay, so we'll be generally working with PWM mode, that is like more than sufficient. We have a programmable frequency which is going to have, like, switching frequency is going to have from 400 kilohertz to 1500 kilohertz, that we have already seen, and the accuracy of this is plus minus 10%. Okay, good. So with this, I think we are good to go ahead with next versions of our design techniques. So let's get into next version. Coming back to this absolute maximum rating, so in any of the dataset, if you read, you have to have this particular parameter in your mind. So what is the input voltage that you can apply at any of the particular pins, or all these pins are there, and their maximum voltage that you can apply, or maximum stress that you can give by your voltage and current, is these parameters. Okay, otherwise if you give more than this, then the IC may get damaged, and IC manufacturer is not responsible for that. Okay, so that's the main reason that try to give these particular parameters. So as you can see, input voltage pin cannot take more than 40 volt. At the same time, enable pin also will be taking 40 volt. LX pin, which is actually the inductor switching pin, so that is going to have a V input plus 0.3 volt. Similar to that, external VCC pin is going to have 14 volt. The BST pin is going to have 42 volt, that is bootstrap pin. we have BST to LX pin is going to have 2.2 volts. You have to understand, like between these two you should not have a exceed more than 2.2 volt. So directly that's the reason they connect it to LX pin with a capacitor. Okay, coming back to BST to VCC pin, it has 40 volts. So similar to that, other parameters are also there, so you can read out quickly. Anyway, I know all these values, so there is no need to go through each one of them, but we have to have an understanding like LX steady current RMS can be maximum plus minus 3 ampere. That's the reason it is going to have maximum 2.4 ampere of current at the output that was given. Okay, good. So we are good to go ahead. Coming back to the next parameters, pin configuration. Okay, so this is very nice, like a TQFN package with 16 pin of 3 mm cross 3 mm, just 3 mm width and 3 mm length. That is the IC size, and as you can see, we have two PGND pin, that is like power ground pin. We have two input pins, that is input supply pin, voltage supply pin. We have one enable pin. We have VCC pin, which is going to have like internal regulator output. We have signal ground and we have mode selection pin. Either you can connect it to like high or low. Low means ground and high to, let's say, 3.3 volt or something, so that you can configure it either in DCM mode or PCM mode. Okay, like PWM mode. Coming back to have soft start pin, we have like a feedback pin, we have switching like switching frequency setting resistor pin, we have reset output, and we have external VCC connector, which is going to get connected by a supply voltage, and we have bootstrap connector, bootstrap pin, and we have two LX pin, which is going to get connected to the switching inductor, and we have one exposed pad that can be connected to my ground. Okay, so if you want to have a detailed understanding about these particular pins, then you can read each and every pin details here. Okay, so that's the understanding that you should have. So pin and then pin name, and we have the description that is required. Understood? So VCC, as you can see, we require 2.2 microfarad of capacitor. So you directly read this and make a note of it, so that you can directly put this into your design. We have signal ground. We have mode selection pin, you can see. So mode selection pin, as you can see here, that if you have to have like connect the mode signal to ground to have a PWM, and connect it to VCC to have it in DCM operation. That's the understanding that is. So mode selection pin can be connected to VCC to have DCM operation, and connect it to ground to have PWM operation. Understood? So this is what the thing is. If you have to have a soft start, then connect a capacitor from soft start to ground. That's the meaning. We have feedback supply pin, which will be feedback pin, which will be like utilizing two resistor divider to set the output voltage to of regulation. RT pin we already talked about. If you want to keep it open, so that you can like save one resistor as well in the design, like you don't have to utilize, so keep it open, then default frequency will be 500 kilohertz. Now coming back to this reset pin, so if you have a reset like utilization of reset, then this is open drain reset output, and this reset output is driven low if my feedback pin drops below FBOK. Okay, and it goes high if it goes above FBOK. Okay, so basically we have, let's say, feedback pin voltage is 0.6 volt, then if it goes below that, then my reset will go low. Okay, so reset will go low, and when my feedback pin voltage goes above this, then my reset will go high. That's the understanding we should have. Understood? So basically you have to have a pull up resistor when it goes high, otherwise it will not be pulled up because it is an open drain mode. Coming back to external bias input, so you have to give a bias voltage to like 2.5 volt to around 12 volt, and we can connect it through a RC filter, so that we can protect the external VCC pin from reaching the absolute maximum ratings. Okay, we have bootstrap capacitor, which we can connect from connect a 0.1 microfarad capacitor between BST pin to LX pin. So if you read each one of them, this is a good idea of like reading the data sheet and applying it to the circuit design and designing your circuit with proper understanding. Okay, So once you apply all these understanding, you will become a very good engineer, hardware design engineer, and there is no doubt about that. Rest one, like you have input capacitor, so minimum input capacitor have to have a requirement of 2.5 2.2 microfarad, but anyway I have been giving you lot of instructions about how to put the input capacitor, how to put the output capacitor. Generally you keep it little bit higher values so that you don't run up into some ripples at the input or at the output. There may be a transient loss at the input side, so or transient like hiccups will be there, or maybe drop down will be there. So that time C input capacitors actually helps you a lot. Okay. There are some typical performance characteristics that has been given by the datasheet manufacturer datasheet itself. So you have like V input 24 volt. You have ground signal ground and power ground to 0. Then VCC has been taken as 2.2 microfarad at the input. BST is 0.1 microfarad. Then a soft start capacitor is taken as 6.8 nanofarad. Okay, nanofarad. And then we have other parameters. So if you can see, we have lot of efficiency curves and all you can see. Okay, so let us say that efficiency we have what I will just tell this as like this. Let us say we have a 5 volt output, okay, and in PWM mode with 500 kilohertz of operation, then you can see input voltage is 6.5, my efficiency is highest, okay. And as my input is increasing, my efficiency is decreasing a little, but up to 36 volt you can see that my efficiency is more than 90%. Understood? So this is the beauty of this particular typical characteristic that is given by the datasheet manufacturers. Okay. So similar to that, other typical characteristics you can have a look on that, but there is no need of that. Like we saw one, like what is efficiency versus the load current, and we have understanding based on the input supply voltage how my efficiency varies. Okay. Similar to that, like we have load and line regulation. So load regulation is actually very important because it is a high current IC. So high current IC, you can see output voltage is, let's say, 3.3 volt, 3.4 volt, and you can see the input voltage has been 4.5 volt or 12 volt or 24 volt or 36 volt. There is no variation at all in so that the load and line regulation is very accurate. Okay, so you can see whatever the current that we are drawing, there is not much difference at all. Okay, similar to that for other voltage output also in DCM mode. This is in PWM mode. In DCM mode also it's almost same behavior. Okay, coming back to the other parameters, let us say soft start shutdown mode. Okay, so let us say we have V output that is going here, okay, and we have enable pin which is always high. Now what happens is once the reset applies, so what will happen as soon as reset goes down, you can see my enable pin has gone down, V output has gone down, and my LX, that current through the inductor, has also went down. Understood? So this is the shutdown mode. Similar to that we have soft start. So soft start, it was shutdown mode, like start with and shutdown mode. So as you can see how it is going to start also, like first enable starts, then after a few millisecond, less than 2 millisecond, my output reaches to the maximum value. Okay, and similar to that the current through the inductor also reaches to the highest value, and you can see my reset has gone high and after that it goes low. Okay, good. So these were all different characteristics that was given by the data sheet. Now let's get into the design phase. So what we will do is let us just directly come down quickly. Okay, so this is very important parameter. Now coming back to the block diagram. Okay, so as you can see in block diagram, we have a proper understanding about what are the different functionalities and different pins. So if you read about this particular pins, you will be able to understand like what are the different items. Okay, so you can see we have VCC which is going to give you 1.8 volts, so you have to directly ground it through a capacitor. That's it, done. We have a signal ground, we have external supply voltage. So if you want, you can keep it from 2.5 volt, let us say, to 12 volt input that we have to give here. Okay. Similar to that, we have bootstrap capacitor pin. So you have to apply bootstrap capacitor through this pin to the like LX pin. So this is the understanding almost, like we have by hearted almost all the design, so that we never miss out any of the like parameter that is required. And this is the internally like integrated MOSFETs, which is going to have like a high side drive and like low side drive to give you the output at the switching node of the inductor. So here is the place where inductor will be connected and giving you the V output, and from here we will be having one feedback pin which will go to FB pin. Okay, so this is my R1, this is my R2. That is how it is going to get connected. You can see there is a FB pin here, so this FB pin will get connected at this particular point. Okay. We have mode selection logics. Whether you pull it high, then it will become like a DCM mode, and if you pull it low, then it will become PWM mode. This is how it was. And this is the open drain like reset. So as you can see, there is nothing connected here. So once you have a open drain output, then you have to have a pull up resistor, then only it will go to give you the reset value as high. Good. So you have now a good understanding about this particular like block diagram as well. There are other pins also, like you can see we have switching frequency setting resistor pin, we have feedback pin that we already told you. Then we have here a soft start capacitor that will be required to like switch on this particular IC smoothly. Okay. Good. Moving on, what we'll do is, let's move to quickly into the detailed description. So detailed description, if you want to really have a very good understanding about like each and every words, you can read about all these, but there is no need. Let's get into the next mode. Going to the mode selection, so PWM operation or DCM operation, you can put the like mode pin as high or as low, and linear voltage is there. Next one, VCC and external VCC. So you can put a capacitor of 2.2 microfarad, okay, to the ground, so that like bypass this VCC to 2.2 microfarad. That is one thing. And external VCC is greater than 2.4 volt typically. Okay, so you have to understand that you have to apply a voltage more than that. Otherwise, one more operation is, it has two inbuilt low dropout voltage regulators that powers VCC. One LDO is powered from Vin LDO, while the other LDO is powered from external VCC. Okay, that's the reason external VCC requires one power supply at this particular place. Okay. So it will tell you, like suppose you do not want to use them, then what you should do is yeah, you can see that if external VCC is greater than 2.4, VCC is powered by external LDO. Okay, and it will help you to increase the efficiency like at higher input voltages. That's the reason it should be powered by external voltage source. Coming back to the other part of this particular IC. Okay. So let us say if external VCC is not in use, then connect it to a signal ground when it is not being used. Okay. Setting the switching frequency, this is very important. Okay. So if you want to set what is the switching frequency that you want to work on, so if you want, you can calculate using this particular formula to what will be the value of RT resistor that will be required based on your switching frequency, that will be in kilohertz. Okay. Otherwise, we have some values that is given by the datasheet itself. So if you want to work for 400 kilohertz, you have to attach 51.1 kilo ohm RT resistor. Okay. If you keep it open, you can have like a 500 kilohertz operation, otherwise 1500 kilohertz for 12.7 kilo ohm. So generally we try to work with open condition itself, like 500 kilohertz. So this is more than sufficient. Otherwise, if you want, you can like always work with 700 kilohertz or 1000 kilohertz, that is 1 megahertz. So these two values I generally like for our application. Even 1.2 megahertz is a good like choice for your applications, but 700 is more than sufficient, or even 500 is more than sufficient. operating input voltage, so actually this will not be needed much, like generally like 12 volt is more than enough for your application. But however, if you want to have a proper understanding what will be my minimum input requirement, what will be my maximum input requirement, based on what? So based on output voltage, the frequency that you are taking, and the on time, that is generally the based on the duty cycle you will be having on time and off time. So similar to that, you have to utilize this particular formula to see what will be the maximum input voltage that can be applied for a particular output. So let us say you are designing a system of 12 volt to 5 volt output. So in that case, you have to understand what will be my minimum, V minimum and V maximum at the input side using these two formulas. Okay, but then generally it doesn't goes wrong, like any voltage input can be sufficient for your output design. Overcurrent protection and all is like not needed, it is always fine. Coming back to the reset output, so reset output, as I already told you, like it goes based on the FB voltage. If it drops below, then it goes low, and if it goes what it says, like reset goes low when FB voltage drops to below this one, okay, and it will go high when it goes above FB pin. Okay, so 0.6 volt is there, so if it goes above, then FB reset pin goes high, and if it goes below, then reset pin goes down. Okay, okay, good. Coming back to the input capacitor selection, so input capacitor selection, if you want to really utilize this particular calculate this particular capacitance, you can utilize this particular formula by using what is my input capacitor RMS requirement. So you can utilize what is the output current required, then what is the output voltage, what is your input voltage, output voltage, all you know, right? So you will find out your IRMS. From that IRMS maximum, you can have IRMS maximum value, which is I out max by 2, and then from here you are going to have input capacitor requirement or input capacitor calculation by using this particular formula, which requires your duty cycle into 1 minus duty cycle divided by switching frequency into efficiency and divided by your delta V in, which is actually allowable input voltage ripple. So voltage ripple allowed will be around let us say 30%, you can say. So 30% you can utilize. Okay, good. Coming back to the next parameter, inductor selection. So inductor selection is very important. Okay, so you have to use this particular formula to select your inductor for the design. So what will be the design? As you can see, my V output is increasing, my L value is increasing. That is the first and foremost requirement from this. Now my switching frequency is increasing, as you can see my inductor value is decreasing. So if you want to use lower value of inductance, or the magnetic size would be lower, in that case you can utilize higher frequency of operation. Okay, but just keep in mind, don't go very high. So I think 500 kilohertz was more than sufficient, or even 700 or 1000 kilohertz. Okay, coming back to the output capacitor selection. So for output capacitor selection, you can go ahead with ceramic capacitors only, that we have already talked about. Even if you want, you can go ahead with electrolytic capacitor also, that is actually good, but it will however it will reduce the cost, but the thing is it will become little bit bulky. Okay, so that's the understanding we should have. So let us say if you want to find out what is the capacitor value requirement, then it will be half multiplied by I step into T response divided by delta V out. Delta V out is the ripple that you are thinking at the output. So basically 3% of output voltage is taken, and a step load is 40% of maximum output current. So basically you can see, let us say 2.4 ampere is the output current. Then what will be my I step? So I step will be 2.4 times 0.4, that is 40%. So 2496, that is 0.96 ampere will be utilized here. Okay, similar to that, T response, you can see like response time of the controller, okay, that you can utilize, and like it will be nanoseconds, something like that, that is already told. So you can see select FC to be 1/9 of FSW, that is your what is that, closed loop over frequency. So T response time will be calculated based on this particular thing, which can be utilized as 0.33 divided by FC. So let us say you are going to use FSW as 500 kilohertz, then my FC will be 1 by 9 times 500 kilohertz, and this value will be utilized here, and you can calculate your T response. So T response, delta V out we have I step, and then this is how you are going to utilize your C output. So C output also generally you can take up 22 microfarad or 47 microfarad. That's the main understanding. Coming back to soft start capacitor selection. Okay, so soft start capacitor selection, how much time do you want to have a soft start? Then you can utilize this particular formula to use this particular soft start settings. Okay, so as you can see, as we increase this CSS value, like as you increase CSS value, my time soft start time also increases. Okay, so if you don't want to have a very big soft start time, you can reduce the CSS values. Okay, so as you can see, like let's say for example, to program 0.82 millisecond soft start time, 6.8 nanofarad capacitor should be connected. Okay, so if you want to use more than this, let's say 1 millisecond or 2 millisecond, you can accordingly put this particular values here, and you will get your CSS value from this particular pin. Coming back to the setting the input voltage lockout. So input voltage lockout, if you want, what will be the input voltage lockout requirement, you can put it here, and accordingly you will get your values of R1 and R2. So see, let us say R1 and R2, and this is my enable pin that has to be set at a input voltage lockout. So for that purpose you have to decide, let us say we have a 12 volt system and we want to design 5 volt output. So we don't want our system to work below 10 volt, then I can set my V input under voltage lockout is 10 volt, and accordingly we can design this particular R1 and R2 to set the enable at this particular under voltage lockout. Okay, coming back to the adjustable output voltage, like we are going to work on voltage regulation. So what happens is there is R top and R bottom. So R top and R bottom, what you can utilize is 227 divided by FC times C output select. Okay, so actually you can utilize this, or otherwise you can utilize this directly. Okay, so what will happen is, one more thing I'll tell you, R bottom can be calculated from R top multiplied by 0.6 divided by V out minus 0.6. So this was the main formula that was used to set the regulated output voltage. Okay, but earlier we did not need to calculate like R top, but right now they are going to give you a formula to calculate the R top value also. Okay, so this, let's say R top value and R bottom value, or R1 R2 value, something like that we used to tell earlier, but now R top and R bottom. So R top also you have to calculate. So what will be the value? 227 divided by FC, that is your crossover frequency that we already calculated, which was 1 by 9th times of FSW, that is switching frequency, and this C out select will be actual capacitance of the selected output capacitor at DC bias voltage in farad. Okay, so what it means is, let us say we have connected an output capacitor, let us say like this. Okay, this is my V output and this is my ground. So let us say we have 22 microfarad, 22 microfarad and 0.1 microfarad, and let's say this is my V output is 5 volt. So as you can see, this is my voltage and this is my capacitance value. So at voltage supplied there will be a reduction. So let's say this is my 5 volt, so there will be a little reduction. So let's say it has become 90%. Okay, so the 90% of 22 plus 22 plus 90% of 22, that you have to add. Okay, and then that will be the total capacitance here. Okay, so you have to put that. So this is how you will get your R top value. Okay, so let us say 90% of these are like Vaishnava, a total say, let's say how much it is, 18 microfarad. So 18 plus 18, let's say 36 microfarad. So this will be how much? 227 divided by 1, let us say this is going to be 900 kilohertz, then 1 by 9th will be 90 kilohertz. So 90k plus multiplied by, this is how much, let's say 18 plus 18 is 36 microfarad. So this is how you are going to get your R top value. So this will come into how much? Total kilo ohm. And according to that, R top value can be utilized here to get your R bottom value. Okay, so we'll do this complete design calculation during our design phase, but right now we'll proceed. This is the main information that needed for our voltage regulation. Okay. Power dissipation, if you want, you can calculate it. Otherwise, there is no need, because it is anyway switching regulator. So like it won't get heated up much. But however, if you want to find out what is your P output, that will be calculated using your output voltage multiplied by output current. Okay. So this is the understanding that we should have. Similar to that, how much power that will be lost during the design. That's the reason we like we calculate generally system efficiency. So this is my system, and we have V input, we have V output. So what is the dissipation across this? That is called power loss. Okay, so that will be actually calculated by P output into 1 by eta, that is your efficiency, minus 1 minus I out square multiplied by R DCR. Okay, so R DCR is nothing but the DC resistance of the inductor. Okay, so that's the reason we selected inductor which will be having low DCR, that is low DC resistance. Okay, good. And if you want to calculate what is the temperature of the junction increase, let us say we have a power loss which is going to get dissipated across the IC, then in that case we will be having ambient temperature plus the junction to ambient temperature thermal resistance. So we have theta j, that is your junction to ambient thermal resistance, multiplied by power loss. So power loss we calculated from here, and then theta j we know from 38 degree centigrade per watt. So you can multiply that. That will be the delta change in your temperature plus your ambient temperature, whatever is there in your environment. That will be your total temperature of the IC at the junction. Okay, so that's the main understanding. So while calculating, we will calculate this as well, like what will be my output power, what will be my power loss, and this is how the total loss. See, higher the loss, higher will be temperature increase. Okay, that's the understanding. Good. So we have given like we have been given printed circuit board layout guideline also, like you have to have the input capacitor as close as possible to the input pin, output capacitor should be like closer to the output pin. Similar to that, all those informations are there, but anyway you can read this while designing the layout to have a better like electromagnetic interference design. Okay, coming back to the typical applications, so we have some 5-6 typical applications. We will see each of the typical application, as well as we will also design our own uh, regulator, which we have already utilized in our several projects for our industrial applications, and automotive applications, and like industrial application as well as consumer applications using this particular IC. But we will be seeing this particular application in our next session. Right now we have understood a complete understanding about this particular data sheet, what were the different information that we needed to identify, and you have a complete idea of how to read the data sheet for any particular data sheet of a switching regulator. Okay, so that you can gather those information while designing your circuit. Thank you so much.